Yesterday we talked about the differential rate laws, which are showing the relationship between concentration and rate of a reaction. And today we're going to do a different type of rate law. It's called the integrated rate law. And this is going to show the relationship between the concentration of something and the time. And they're going to be a little bit different depending on which order they are. So we're going to start with first order, meaning, and then in this case we're going to have a single reactant. And you can see that the integrated first order rate law is this equation right here. You don't have to memorize that. In fact, this one is in your reference packet. It's written just a little bit differently. So if you subtract natural logs, you can move it to the other side, but it looks a little bit different, but it's the same equation. So you don't have to memorize it. You do have to know that natural log is related to first order. And then they rearranged it to get this one here. So these two are the same reactions. I don't know how much you guys know about natural logs, but it's okay if you don't know how to do the math with them. You just have to know how to use this equation for this part of it. So first of all, there's two different A's in brackets, and remember brackets means concentration. A with a little subscript 0 means A at time 0. So this means the initial concentration of A, and then the bracket A without the 0 is saying A at a new time, so the new concentration after time has passed. And I want you to notice that this is actually a linear equation. So if you go way back to your algebra days, we have y equals mx plus b. So remember, this is the slope, and this is the y-intercept. And then you have your x-coordinates and your y-coordinates. So in the case of the first order rate law, natural log of the concentration of A is on the y-axis. Time is going to be your x variable, and then you have negative k, which is going to be the slope. And then the y-intercept is the concentration of A at time 0, which makes sense because the intercept is when it crosses the axis, and so that would be at time 0. So what you can do is to use this, you can plot this if it's first order, and when you plot the natural log of A, so all of your natural log of A numbers will be on the y-axis versus time on the x-axis, you're going to get a straight line. And so sometimes on the AP exam, they'll give you a lot of information, a lot of data, and ask you whether it's first order, second order, or whatever. And one way you can solve for it is the method of initial rates that we just did in the last class, but this is a different way. So if they give you a bunch of concentrations and a bunch of times, you can plot the natural log of A versus time and see if it's a straight line. And if it's a straight line when you have natural log of A, that's going to be first order. Keep in mind that you don't always do concentrations. You can also do pressure or mass because those will change as the reaction proceeds as well. You also need to know about half-life, and you probably have talked about this in other classes. I know you did a little bit in honors chemistry, but half-life is the time that it takes for half of it to happen. So in this case, if you're trying to do a reaction, the time that it takes for half of A to turn into B. And you can solve for it by plugging in what I have circled in purple right here. So if the concentration of A equals half of the initial, so the initial concentration divided by 2, then you can substitute that back in for the concentration of A. Don't worry too much about deriving this equation. It's okay if you don't see the math for how I got all this. The main thing you need to recognize is that this is the half-life for a first order reaction. So first of all, notice that the only things you have are the half-life and K, because natural log of 2 is a number, it's 0.693. So in this case, the half-life does not depend on any of the concentrations of A. So if they give you K and ask you what the half-life is, you can solve for it. Or if they give you the half-life and ask you to solve for K, you can do that easily. And this equation is also given to you in your reference packet, so you need to be able to use that. But just recognize that it's a first order half-life because it doesn't say in the reference packet that it's for first order. All right, the integrated second order rate law is the same as the first one. It's y equals mx plus b, except the difference here is that we're going to do 1 over the concentration instead of natural log, and notice that the negative sign is gone from right here. So those are our two main differences. For second order, it's 1 over the concentration, and for first order, it's natural log of the concentration. So again, you can graph it. So if they give you a bunch of concentrations of A, you can graph 1 over the concentration of A versus T, and you'll get a straight line with the slope of K. And then they're also giving you the half-life equation. Notice that this one has concentration of A. The initial concentration of A is actually involved in the half-life equation. So there's one more variable in this one than there was in the first order. And that's kind of what this next part is saying. That note that for the first order, half-life only depends on K, but for second order, it depends on both K and the initial concentration of A. And also for first order, the half-life will stay the same throughout the whole reaction because all it depends on is K, whereas for second order, it's going to change, and each successive half-life is double the preceding one. And then the last order we're going to talk about is zero order. This doesn't happen very often. It's sometimes going to happen on a metal surface or with an enzyme. And for this one, the rate is constant. It does not change with changing concentration. And that is because of this down here that I wrote out. Notice that for zero order, you would have rate equal, this is the differential rate law, rate equals K times the concentration of A raised to the 0 power, but anything to the 0 power is just 1. So really K just equals the rate. So it's not going to change with the concentration. And they also gave you the integrated rate law for this one. Notice that it's still y equals mx plus b, except this time you don't have natural log or 1 over. You just have regular old concentration. And then they're also giving you the half-life. And all of this can be summed up in this table down here that we're going to get to in just a minute. It also, letter D is just talking about if you have more than one reactant. Usually we focus on the one that is the most significant, just to keep it from getting complicated. And like I said, 12.5, this table right here is super helpful. So hopefully you either printed it out or can jot that down. It's basically just showing you all the different rate laws. So you've got the differential rate law, the integrated rate law. It's telling you what to plot to get a straight line. So if you plot that and you get a curved line, you know it's not that order. That's one way you can figure out the order. And then it also gives you the half-life equations for each one. So you're going to use this a whole lot for your progress check. The ones that I have circled in yellow are the ones that are on your reference packet, so pay close attention to those because there's a good chance the AP exam would expect you to be able to use them, and they don't label them on the reference packet. I wish they would say this is for first order or second order. All it does is just write the equation, so you have to still know that natural log is for first order and 1 over is for second order. And you also have to know that that half-life equation is for first order. The rest of the equations you don't need to memorize, but you do need to know what to plot, and you need to be able to use them. So if they gave you the zero order integrated rate law in the question, you'd need to be able to use those. And that's it for this section.